Sorry about that. So yeah, I'm Assumption from Queen Mary University of London. So I'm talking about measuring the propagation speed of gravitational waves with laser. Yeah, you can find the works on archives. So here are all the people working together in the cosmology working group of LISA. Okay, so let's start with the motivations. So we know that we have a constraint on the gravitational wave speed by this binary neutron star events with electromagnetic counterparts. This constraint is very tight, so the deviation of CT, the gravitational wave speed from C, is smaller than 10 to the minus 15. However, there's a caveat that this measurement happens at the merger of BNS, which is in the order of 1,000 Hertz, but we don't have data now to constrain the GW speed at a low frequency scale. So it could be that some physics happen where CT travel slower than C. So here is an interesting model. It's an effective field theory model of dark energy. So there's an operator in the action that predicts a scale that is called a UV cutoff. So at a high energy scale, larger than the cutoff, then gravity follows general relativity. But at lower energy scale, corresponding to low frequencies, so there's a coupling field to the gravity that makes the CT travel slower than the speed of light. So as we know, we can detect massive black hole mergers at laser bands. So it is a good indicator for us to test the theory of gravity here. Okay, so let's start with theoretical framework. So we write down GW propagation equation. So when CT is 1, then it is the GR propagation equation. So now CT is smaller than 1. So we find that the CT modify both amplitude and phase of the waveform. So we can separate them and study amplitude and waveform. So the most important things that has been changed in when introducing CT is an extra factor of CT in the relation of frequency in observer and the source frame. So it will lead to the difference in the waveform. So if we take the derivatives with respect to the frequency, with respect to time, then we can find an extra factors here. So it is some combination of delta, which is 1 minus the ratio of CT in observer frame and the source frame. So there's a delta and the frequency derivatives of delta. And this is the usual redshift relation. So we can integrate the inverse of these derivatives and get time before merger, and integrating it again, we can find a phase. So here's how we find a phase. So here we include post-Newtonian expansion up to 2.5 PM order. And we also find the modification to the amplitude. So this is the gravitational wave luminosity distance. So it is the usual luminosity distance multiplied by also an extra factors depending on CT. And replacing the luminosity distance by the gravitational wave luminosity distance, we have this usual GR combination with MO to be the observed chirp mass. And there's also an extra factors of this ratio in CT. So here we consider only the propagation effects on the waveform, and there's now there is no waveform model for modified gravity yet. So we don't know what happens at merger and ring down. So, but we assume that it can be modified in the same propagation effect here. But to be conservative, we here only show the Fisher matrix forecast with in spiral waveform only later. So let's look at the n source of CT. So first we use a polynomial n source, which is an expansion of CT in a series of frequencies. So here f over f star is a small number. So f star is a frequency scale outside this band. So we have this small number. So when f star is higher than this band, then we have the positive power. And when f star is lower than this band, we have negative power. So this is always small. So beta 1 and beta 2 controls the deviation. And the second one is CFT-induced N source, which is a Fourier-based model. I saw it in the motivation. So it is a more complicated form, but it also has a frequency scale f star here. But this is within the laser band, so CT transits within laser band. So here is a more direct image for this formula. So we see a transition happening around the scale of f star. So C naught is a constant values at the low frequencies. So CT is a constant lower than speed of light here. So after transition, it become 1. So here is a plot of delta, which is 1 minus this ratio of CT. So we see it is zeros on both sides because CT is constant here. So it goes through peak values when the transition happens. So let's look at how the waveform is modified in the plots. So we take the negative polynomial k as an example here. So we take some exaggerated values to visualize the effect. So the power is negative, so it means f star is lower than laser band. So let's look at the amplitude plot first. So we can see a deviation between the modified waveform and the GR waveform here. So the black curve is the noise curve of laser. So we can see the deviation become larger at low frequencies because it is closer to f star. So we can see a lower, the higher mass system can show a larger deviation here because it has a lower frequency. So it's similar in the phase. So the phase expression in a Poisson-Newtonian expansion looks like this. And the correction and modification comes into the factors here. So we can see a similar features at low frequency. The deviation is larger. So we perform Fisher forecast to the waveform. So we're still using this example. So we'll estimate the parameters of redshifted chirp mass, the symmetric mass ratio, redshift, and TCM size C are Newton parameters in the phase, and beta 1, beta 2. So we assume 30 days of observation before merger. So here is a selected contour for some parameters. So we can see the chirp mass and the redshift. They have a good constraint here. And look at beta 1, we have a constraint in the order of 1. It is decent. But we have a weaker constraint in beta 2. It's a few hundreds. So this is likely due to the second order terms. It is quite a small number. So we make it difficult to constrain beta 2. So this is also why we only stop at order of 2, because the constraint will be much weaker if we expand to higher order. And we also observe some high degeneracies here. This could be due to these parameters. They are all appear in the phase. So it is, they are quite degenerate. We also compare the Fisher forecast with MCMC simulation results. So we take a system of this, and it has an SNR signal to noise ratio about 1000. So it's a quite high SNR. So we can see they agree quite well, the Fisher forecast and the MCMC. And yeah, we find good agreement. And in a lower SNR case, the constraint, the level of constraint is generally the same, but we can see a shift in the for MCMC, the center of the contour will shift a little because has a low SNR, but in general, it shows that our Fisher forecast is quite robust comparing to MCMC results. Okay, here's a plot to show you the constraint on beta 1 on top of the SNR contour in red in a parameter space of total mass and redshift. So it means, yeah, the different system with the total mass and different redshift will give us a different constraints. So we can see the constraint goes from 100 down to 1 across the space. So we can see a good constraint will come from system with 10 to the 5 solar masses, and lower the redshift, the better the results. Yeah, we can see it generally follow the SNR contour here. And we also show the peaks of the massive black hole population in 3 models: POP3, Q3 no delay, and Q3 delay. So the POP3 model predicts a lower mass massive black holes. So it will give up a bad constraint if the model the population follow the model. But if the population follow Q3 models, we have more events taking place within this region, so it can give us more sources to make our constraint better.
And so just to say you have a few minutes left.
Yeah, thanks. So yeah, if we can combine multiple sources in all the 3 models. So here is some population density across this total mass and redshift space. So it shows you some population density. We can see Q3 model, most of the massive black hole population has a medium range total mass. So when we combine all the Fisher constraints together, we find that the constraint on the beta 1 or beta 2 values is as good as the one from one golden source, which means if we have multiple sources and combine together, even we don't detect the best constraints from one source, we can still get a decent constraint from multiple sources. Right, so at last I will talk about EFT induced case. So let's remind you the complicated formula here. So if we look at the plot, we can see similar features as the polynomial case. So if we take a transition at around 10 to the minus 4 Hz, then we can see before the transition, the waveform is different from GR, but after the transition, because CT become 1 again, so yeah, it's the GR waveform here. So similarly, the base show the similar features here. So if we look at the plots of the constraint on C node and F star, we can find the constraint, the order of constraint is quite good for C node and F star here. So C node error in C node is just about 10 to the minus 4 for the best case. And the relative error on F star is 1%. So these are quite good for the system with mass of around 4.5 solar masses. So we can see the best constraint shifted a little from the SNR contour. So this means actually the transition take place in important parts. So if the transition take place just in the middle of the in spiral stage of the waveform, and the waveform is inside the laser band, then because this in spiral stage will stay for a long time, so it will give us much information about the waveform, so it can give us a better constraint on these parameters. Okay, great. Let me summarize. So our work established tests of GR in weak field limits with gravitational waves. So it will extend the constraint on CT to low frequencies. So we introduced two answers for CT with two modified gravity parameters, beta 1, beta 2, and C0 and F star for polynomial case and EFT induced case. So a typical constraint on the beta 1 in polynomial case for a typical system of 10 to the 6 solar masses at ratio of 1 is in the order of 1, but we get a weaker constraint on another parameters, beta 2. And finally, in the EFT case, we find that the C0 and F star can be constrained quite well if the transition of CT happens in the laser bands, but it would get worse if the F star transits outside laser band or close to the bounds of the laser band. Yeah, that's what I want to talk about. Thank you very much.
Thank you very much, Hanson, for this very interesting talk. So we're a bit over time, but we started a bit late due to technical difficulties. So I don't know if the audience has questions. You can either raise your hand or type them in the chat. I don't see a question for now. So I have one myself. I think you said it, but I did not fully catch it. To what extent is modification, does a modification appears as a modification of PN coefficients, and to what extent does it create real new terms?
Yeah. So we find that all the correction is in the known PM orders. So yeah, in some cases, for example, in the negative polynomial cases, it could appear the lower PN orders, which is lower than 0, which is not appear in GR. So yeah, it creates some new post-Newtonian terms, and it actually can help us to constrain the models, because new PM orders would be a big change in the waveform. So is it
okay? I see. So the structure is actually changed. It's not only modification of existing contributions. Okay.
Yeah, yes.
I see. Okay. If there is no more, there are no other questions, I think we can move on. And thank you again, Hanson, for this talk.
Thank you.
So Janis, if you want to share your screen.
Sure. Let's see whether I have better luck with the technical side. How is that looking?
Good. I see your screen, your slides in full screen. So
perfect.
This next talk is going to be by Janis Noller from University of Portsmouth and the University of Cambridge. And it's going to be about probably the speed of gravity with LBK, LISA, and joint observations. The floor is yours. You have 50 minutes, so we give you a cue at -1 minute.
Perfect. Thanks a lot, Sylvain. And thank you for the introduction. Thank you for having me. And especially also thanks to everyone for being here on the last day of the workshop. So I'm kind of in a very privileged position here in that Hanson has perfectly set the scene also for my talk, as you heard from Sylvain. I'll be talking about also probing the speed of gravity, but on a slightly wider frequency range. So both considering observations and forecasts for the LIGO-Virgo-Cagra band, the LISA band, and also intermediate frequencies, so joint observations. And the majority of what I'll talk about is, I don't know whether you can see my mouse, is in this paper here with Ian Harry from the ICG in Portsmouth. And you can find more information in this archive identifier here. So I would like to start by, I guess, expanding a little bit on what Hanson said in terms of the motivation. and really reminding you why this is interesting in the first place. So like Anson said, of course, we already have exquisite constraints on the speed of gravity, on the speed of gravitational waves from about 5 years ago, GW 1708-17, binary neutron star merger. We got these exquisite constraints at the level of 1 part in 10 to the 15 on the speed of gravity. But one important assumption that went into these constraints is indeed assuming that the speed is frequency independent. So in terms of the plot you're seeing here, where I plot the speed of gravitational waves versus frequency, this would just be some horizontal line. It would have to be very close to the speed of light, given the constraints from GW 1708-17. But what kind of Amsa has already motivated, what I'll try to convince you of and give you a little bit more intuition about here is that actually for the kind of theories of interest here, namely the ones where the speed of gravity in principle is different from the speed of light, especially at low frequencies, so to the left in this plot, it's very natural for this to be frequency dependent. And so to get a transition that looks a little bit more like this. Now, your knee-jerk reaction to this may be that you feel that this looks like you're bending over backwards to satisfy the bound from GW 1708-17 and to create some interesting phenomenology, pull it out of a hat for lower frequencies. But what I really want to emphasize is that this is actually very, very natural in these kind of theories. And so let me try to give you a little bit of intuition here. One of the main motivations for considering different speeds of gravitational waves at low frequencies are these dark energy theories. And there's a big class of them where the speed is indeed different from the speed of light. And generically, what happens there is that at very low frequencies, in fact, the speed can be different from the speed of light, but again, it is frequency independent. So you recover this sort of asymptotic horizontal line at low frequencies, which can be offset from the speed of light. But as you move closer to the LVK band, there's a special scale in this theories, and the special scale is a little bit like the Planck scale in general relativity, where in general relativity, the Planck scale tells you lots of things, but one of the things it tells you is where the theory breaks down. You know that once you approach energies which are close to the Planck mass, the theory becomes non-unitary, it becomes ill-defined, and you need some new physics to come in to save the day. And this is, of course, the infamous search for quantum gravity. So in these dark energy theories, there's different coupling constants, different scales. And it so happens that the analog of this scale sits in the LVK band. And if you convert that energy scale to a frequency, it sits at around 10 to the 2 hertz. And so just as in the GR story with the Planck mass, you know that some new physics needs to come in around 10 to the 2 hertz for these dark energy theories to save the day and to make sure that they become wholesome again. And so, of course, we don't really know what this new physics is, just like we don't know what the true theory of quantum gravity is in the GR context. But there's a sort of very fundamental intuition you can have. If this new physics is Lorentz invariant at a fundamental level, and the solutions are Lorentz invariant too, then that will naturally lead to the speed of gravitational waves transitioning back to the speed of light. And so this kind of picture you're seeing here is a very generic and natural picture in dark energy theories that affect the speed of gravitational waves at all at lower frequencies. So this is kind of the basic intuition why this is not just something to cook up to have something interesting for phenomenology, but it's really something that's fundamentally very well motivated. And there's this nice paper that I'm highlighting at the bottom here by Claudia and Scott that kind of tells the beautiful story behind this. Okay, so we would like to constrain these kind of frequency-dependent speeds of gravitational waves. And of course, we need some kind of ansatz. You already saw some examples in the previous talk. That parameterizes this, some parameterization for the speed. And so we're coming up with something here that has, again, quite a beautiful story hiding behind it in terms of the link to the underlying fundamental physics. I'll cut that short here in the interest of time and just give you the answer that parameterizes the speed of gravitational waves here. And you can see it's this ansatz at the very bottom, which only has 3 constant parameters. The first one, this delta CGW, is basically telling you what the step size is, what the offset is between the asymptotic speed of light at high frequencies and this asymptotic speed of gravitational waves that's different at low frequencies, so the cosmological motivated one. Second parameter is F star. Again, it's a parameter you saw in the previous talk as well, which is the kind of the frequency where this transition takes place. In terms of the fundamental physics, this corresponds to the energy scale where the new physics is coming in that causes this transition. And finally, there's a sigma parameter, which basically, in terms of the template, tells you about the steepness of this transition, how quickly it takes place. And again, this encapsulates a lot of the underlying physics from whatever new physics is causing this transition. So you have this fairly simple 3-parameter template, and now we would like to confront this both with data from LIGO and with forecasts from LISA and similar observations. Okay, so before actually confronting this with the data, I want to just take one moment to think a little bit about what kind of physics is actually driving these constraints. And I want to tell you this with a very simple example. So suppose we have some frequency-dependent transition, a little bit like in the top left corner here, where the speed of gravity increases with frequency, some lower value at low frequencies, and then goes to some higher value as you go to higher frequencies. Now, think of some typical compact source that you may see in LISA or LIGO Virgo Cagra or a similar detector. Of course, the source is not monochromatic, but what really happens is that earlier on in the in-spiral, you get signals that of a lower frequency, and later on in the in-spiral, the frequency increases, the pitch goes up, and we get higher frequency signals. So with a frequency-dependent transition of the speed of gravitational waves, what will happen is the signals that are sent out earliest are traveling slower than the signals that are sent out later on when the frequency of the wave is increased. And you can get into this, well, funny, if you like, situation, really, where the speed difference is large enough that the signal parts that are emitted later on in the in-spiral are actually catching up and, in principle, overtaking the earlier part of the signal on the way to the observer. So in principle, you can get a situation where at the observer, you actually see the merger before you see the in-spiral. Now, of course, that's a drastic example, but just from this kind of back of the envelope calculation, just to give you some intuition, for a source that sits at around 400 megaparsec or so, just a shift in the speed of gravitational wave by around 1 part in 10 to the 9 shifts the signal by over a year. So once we get to shifts by 10 to the minus 8 or so, that's really something you can constrain just from the fact that you see mergers before you see the in-spiral. And of course, we can do much better in terms of gravitational wave analysis. We can work to much higher precision than this. But just to give you some intuition about the underlying physics that drives a lot of these constraints. There's many other different types of effects that you can also take into account and use to constrain the speed of gravitational waves and their frequency dependence. But this is the one we find to be the most constraining in the cases we look at. Okay, so let's first look at real data constraints from the LIGO band. And so I want to start by sort of looking at a simplified example where we have a transition a little bit like this here, where it's just the very tail of the transition that kind of leaks into the LBK band. And in that case, we can simplify the template and we just have the difference in the speed of the gravitational wave from the speed of light at some reference frequency and then some fall off with the frequency as we approach the speed of light. So this is kind of a simplified version of the template that just comes out of a Taylor expansion in that tail. Now we can run a full Bayesian inference code with the data from GW 1708-17. And you see kind of all the different points that are accepted in running this inference code here for evaluating the difference in the speed of gravitational waves from the speed of light at a reference frequency of 30 Hertz, and for different values of this steepness parameter, this power law parameter. And so you immediately see that just from this one observation, GW 1708-17, we can bound the speed depending a little bit on the steepness parameter, but roughly at an order of 10 to the minus 17 or better for higher powers of sigma here. And so that immediately tells you that even for mild frequency dependence, you immediately get significantly stronger bounds than for a purely frequency independent speed, where the bound was around 10 to the minus 15 in the case of GW 1708-17. We can also do something which is a little bit more analytical and which will be useful for the forecasts, which is instead of running the full Bayesian inference, which we can do when we actually have data, we just approximate the exclusion capability that we have. And we can do that by computing this so-called distinguishability criterion here. The experts in the audience will recognize this as a noise-weighted inner product from the residual of the parameters here. But the people that maybe for whom that's not so familiar, I can give you a little bit of intuition about what's happening here. Really, what you're doing fundamentally is you're taking some fiducial waveform, some general relativity waveform, and now you're kind of dialing up this modified gravity parameter, in this case, the deviation of the speed of gravitational waves from the speed of light. And you keep dialing it up to the point where you find that the waveform has morphed so much that with the detector sensitivities that you have for a given detector, you can tell it apart. And so the line in this plot that kind of corresponds to what we have on the right is the top line here. That's also for a reference frequency of around 30 Hertz and for the advanced LIGO detector. And you see that this exclusion line here lines up relatively well with the exclusion from the data, with a little difference, namely that this here is about 1 to 2 orders of magnitude too optimistic, which is not so surprising because this way of estimating the exclusion capability ignores any correlations between the different parameters that this full Bayesian inference model takes into account. But the point I want you to take away is that this kind of approximate exclusion capability is getting the ballpark right in comparison with the real data comparison. Very good. Okay, so until now, I've kind of given you the simplified template where we're just working in detail. Now let's really go to the full template. And I'm plotting the results in a slightly different way here. I'm plotting a parameter space where on the y-axis, we have the steepness parameter. Here we have the central or the reference frequency. Sorry, not the reference frequency, just the central frequency associated with this transition here. And in this color plot here, I'm basically telling you at different points in this plot how well we can exclude, to what level we can exclude deviations in the speed of gravitational waves from the speed of light. The contour lines correspond to 1 part in 10 to the -3, -6, -9, -12, and -15. And this year, I'm focusing on frequencies just in the bottom of the LIGO band all the way to a little bit below the LISA band here. This is what you get just from a single observation of a GW 1708-17-like event in the LIGO band. And something that you see...
I'm sorry, you have a few minutes left.
Okay, I'll need to speed up a little bit. Thank you, Sylvain. Something that you see that's very powerful already is just from this single observation in the LIGO band, you find very strong constraints all the way deep into the LISA band for sufficiently slow transitions. Now we can run a similar case for just a collision of supermassive black holes in the LISA band. Again, just a single event, one of these golden events, as Anson was calling them. And again, you see that deep in the LISA band, we get constraints up to 1 part in 10 to the 17 or better. So very, very strong constraints, again, just from a single source. And finally, we can just put these two events together, and we get this constraint here, which massively constrains the speed of gravitational waves all through the LISA band and a little bit below and above. And of course, I'm just cutting out the LIGO band because, as we saw before from the data, that's already very, very strongly constrained. Okay, so let me speed up a little bit just so Sylvain doesn't shout at me. The one thing we can do here is we can also, instead of doing this for LVK and LIGO, we can forecast how this would work for something like the Einstein telescope. And so you can see that the bound on the left, the GW 1708-17-like observation, that gets tightened as I go to the Einstein telescope. And similarly, on the very right, we even further squeeze this parameter space and find these constraints, even stronger constraints on the speed of gravitational waves. Okay, now the final point I want to make in the last 2 minutes or so that I have is that there's kind of this plot is fantastic and really nice. It gives us very, very strong constraints on the speed of gravitational waves in this space of parameters. But there's sort of a sore spot, which is this top right corner here, which corresponds to very sharp transitions where the sigma parameter is quite large. That happen at around 1 Hertz. So just in the sweet spot between the LISA and LIGO bands, so that observations there can't constrain it very, very well. And a complementary way of constraining this is looking at multi-band constraints. So this is sources like GW 1509-14, which corresponds to this black line here, which are in principle visible in the LISA band and later on in the LIGO band. And there, one thing you can do is you can very accurately predict from the observations in the LISA band when they will arrive in the LVK band. And you can do that roughly with an accuracy of around 10 to the 5 seconds, or in human units, this is around a time scale of a day or so. And so that means that if you don't see the event at that time, that's kind of a smoking gun signature for something interesting having happened here, a transition in the speed of gravitational waves in this island that was unconstrained previously. And so that means for a source like GW 1509-14 to be detectable in the future, these multi-band constraints can in principle constrain this delta CGW up to 1 part in 10 to the 12. Okay. I will skip this slide here just so that we have a little bit of time for questions, hopefully. And I'll just go straight to the conclusion slide. So just let me emphasize, number one, we can actually constrain these deviations in the speed of gravitational waves very, very tightly already with single golden observations in the LVK and LISA bands. There's some small region of parameter space that's unconstrained by this and very interesting also for future observations like edge or so. And we can also constrain that very tightly with multi-band observations. And finally, you should really think of these kind of frequency-dependent transitions as something very well motivated from underlying fundamental physics. So in some sense, watch this space for when more and more observations come around. Hopefully, we'll learn much more about the underlying physics in the process as well. Thank you so much.
Thank you very much, and this was a very nice talk. It was a nice synergy between the first two talks, I find. So we have a little bit of time for questions. I haven't seen any question in the chat so far. There is one from Jemison. Go ahead.
Mm-hmm.
Hi, Johannes.
Yeah,
Just a question about redshift. Did you include the redshift, and what is its role? What do you think it is the role of the redshift? Because you talk about supermassive black hole binaries that could be at high redshift.
Yeah, that's
so
right.
In all your idea, in all your approach, what's the role of the redshift in your opinion?
Yeah, so for the one thing I should say maybe up front is, of course, the plots I'm showing here are kind of for just a single event in the LIGO band or in the LISA band. So that's something that make it improved with more events. For the redshift, so here we're really considering supermassive black hole, a binary merger where the masses are roughly 10 to the 6 solar masses, so something like Sagittarius A. And if I remember this correctly, we placed them at a redshift of 0.1. So that was the redshift that we had there for that representative event. If you move the redshift around, of course, that can modify the constraints a little bit. But here we're really thinking of order of magnitude constraints. So I guess even if it's a little bit further away or so, or a little bit closer, I'd be surprised if that changes things dramatically. I think the order of magnitude is really what stands here.
Okay, thanks.
All right. I cannot see another question, but I will have one myself. Actually, could you comment on is there any modification to the two-body problem itself and to the evolution of the dynamics of the binary to be considered when you consider these theoretical modifications? Or is it a pure propagation effect?
Right, so that's an excellent question, actually. So in principle, there's lots of different effects, right? So you may have spotted that really the effect behind the constraints that Anson was talking about and that I was talking about, that's different types of propagation effects. But there is really also other further effects that you may use. And so one thing that we looked at early on is really something that's an intrinsic source effect, if you like. So for example, the fact that the speed of gravitational waves is different, that does leave an imprint on the power emitted in the binary in the first place, for example. And you can also use that to place constraints, but they are much weaker than what you have here. They're at the level of 10 to the minus 2, maybe if you push it 10 to the minus 3. So I guess it's one thing that I guess is a challenge in all of these things is thinking of all the possible effects and some phenomenology like this could have, which is lots. And then you sort of need to hierarchically order them in terms of what gives you the strongest constraint. So yes, but at least the ones that we could think of are systematically weaker than this kind of propagation effect in terms of bounds.
All right, thank you. If there is no other question, I think we can thank Johannes again for this interesting talk and move on to the next speaker.
Thank you very much.
So Chantal, if you want to share the screen. So we see your video. Do you want to share your screen?
Yes. Okay, can you see it full screen? Yes. Okay.
Okay. Right. So Chantal Pitt is from CA in France. Is gonna talk about the detectability of modes with LISA. So you have 15 minutes, and I will tell you 3 minutes in advance before the end.
Okay. Okay, thank you. Thank you very much. Well, yeah, first of all, thank you for having me. This is my first conference, so I will try to do my best. So yes, my name is Chantal Pitt. I'm a first year PhD student at CEA-Saclay and also in association with Université Paris-Saclay. And today I'm going to give you some insight on the detectability of modes with LISA, which is work carried on with these collaborators shown here. So, sorry, I cannot move. Yeah. So I will start first with my motivation, and this is a plot that many times have been shown. So I'm not going to go into the details, but just remind you that we expect to see very high signal to noise ratio of the massive black hole binary sources. And so the idea is that with this very high SNR, we should be able to test the no-Her theorem, right? It states that any black hole can be described by the mass and the spin. And into doing this kind of test, we are actually testing general relativity with quasi-normal modes. So this is the main goal, let's say, for my thesis. But let me start first with our ability to even detect or differentiate different modes, right? And modes from the complete waveform, so the spiral merger ring. So as you probably know, the waveform of compact object binary can be divided into 3 stages: the spiral, the merger, and the ring. Now, the spiral is when the 2 bodies start feeling the gravitational pulling to one another, so they start falling into one another. And these dynamics can be very well described by the post-Newtonian, where you include high orders of the velocity. Afterwards, we have the merger, where the 2 bodies combine, let's say, into one. And the only way to resolve these dynamics is by actually solving Einstein's equation, and that's where numerical relativity comes into play. And then finally, when we have the final black hole, it will relax into more stable state, and this is described by perturbation theory. So if we only assume this last stage, so the Riemann model, in perturbation theory, then we will have a perturbed black hole, and in the de-excitation of this black hole, it would emit gravitational waves that can be written or decomposed into quasi-normal modes. Now, the reason they are called quasi-normal modes is because of the boundary conditions that you have on the wave equation, and so your frequency will no longer be real, but it will acquire an imaginary part. So you will have a complex frequency that has the frequency and the damping time, right? And each of these frequency is actually labeled by the L and the M as the polar and azimuthal angular number. And here I'm just showing you an example of these quasi-normal modes in a source that could be in a source from the Lisa band, let's say. And you can see the strain of all these modes and also the addition of all these modes, which is represented here in black, in the time domain. And so the idea is that we know all the values of this frequency, either the real part and the imaginary part. And actually they are cataloged, for example, by Berti and collaborators in this paper here. And what you can do is, once you know those values, you can actually make a connection with the mass and the spin. And a way of parameterize that is also given in the same paper of Berti and collaborators, and it's given in these 2 equations here. So a more visual representation of that, if you will, is given in a paper written by Gossan and collaborators, which is the plot I'm showing you here on the left side. You have the mass versus the spin, and with this kind of equation, you could see like all the values that you will get with the known frequency and damping time. And as you can see, when you have more than 2 modes, then you should be able to pin the mass and the spin, and that you do when you look at the lines. For example, here you will see that they all intersect at the real value, which is denoted here with this blue diamond, right? Now, if, for example, you were to have a deviation from these frequencies, then you will see what is on the right side, on the plot on the right side, where you have a deviation, where all the value of the mass and the spin will be shifted. So this is the main idea behind the testing of no-Her theorem. But as I said, we first want to know, or we want to test our capability of detecting this modes, let's say. So what we do is we try to compare different models with different quantity of modes in a Bayesian analysis, and for that we use the Lisa Beta software, which created by our chair here today, Sylvain Marsat and collaborators. And it takes phenomenological waveforms, either from PhenMD, PhenMHM, or the effective one body with high modes, and reduce all the modeling, which just to make the waveform faster. And then it passes through the Lisa response. So you have to take into account, obviously, the orbits of the constellation, the delays between the different references frame, and also the TDI, which is the time delay interferometry for either first or second generation. And then as a sampler, I use Dynasty. I know a lot of people like to use better the PTMC, but in this case, we wanted to compare models by this bias factor, which is just the ratio of the evidence. And the good thing about Dynasty is that it gives you the evidence directly. So it's more easy to use, right? So our procedure is that we injected a source with that we create with a PhenMHM. So we take into account 6 modes, which are the ones written here, which are the ones allowed by this software. And then we wanted to make the scenario the more real case scenario possible. So we use the second generation TDI. We also take into account the full response of Lisa. But then we also use a rescalization just to eliminate frequency-dependent perfectos that were common to the signal and to the noise. And as a source, we choose the Lisa Data Challenge Sangria catalog, a source that was in there that had a signal-to-noise ratio of 725, which by a recent talk that I heard from I don't remember the name right now, sorry. It was in the mean, so it's let's say a good source. And one thing I had to mention is that this kind of PhenMHM and PhenMD do not allow for precision, so it only allows you to have aligned spins, right? So these are the source of our parameter, and with those parameters, the source will look like this in this frequency domain, where you can see clearly the contribution of all the different modes listed here, and also the final addition of all of them, and also the noise, right? This noise is the science requirement, science requirement document noise. And once we have the signal, what we try to do is we let our code, our sampler search for different kind of models. So in the first model, we only have one mode, which is the 2-2, which is the most relevant one. Then the second model have 2 modes. Well, you can see that here we add the 3-3 and so on and so forth, up to 6 modes. So we let the sampler run, and finally we got our results. And here we decide only to show you like the most important parameters to test the Noether theorem, which are the intrinsic one, right? So we have here the parameters of the spin of the 2 masses, the chirp mass, well, it's actually the logarithm of the chirp mass, and also the mass ratio, which in this convention is always bigger than 1. So the mass 1 is bigger than the mass 2. And what you can see is that the posterior distributions for the 3 different models. So with 1 mode, 3 modes, and 2 modes. And as you can see, the model with the 6 mode is almost perfect to the true value. And just to compare, I put the tables here with where we have the true value and the estimated value with the model of the 6 modes. And also, if you want to compare this by a bias factor that I've been telling you about, where it's only the ratio of the evidence, then you can see that the values is always negative, meaning that the analysis prefer the model of the 6 modes instead of all the other ones. And then we did the same thing, but let's say a more even realistic case where we inject also the noise in the signal. And then we also look for different modes. And here I wanted to show you only the 4th, 6th, and 6th modes, because here something kind of weird happened, and the model with 4 modes actually finds the true values better than the other ones. This is a preliminary result, so we are still trying to see why this is happening. But here I'll show you again in this table the true value versus the values estimated with a model of 4 modes. And yeah, once again, in the bias factor, you can see that at least up to the model 3, the model 6 is preferred. But if you want to compare with the 4th and 5th, this is still like something we need to see and take into account. And so with that, I'll go to my conclusions, is that we can do parameter inference with high accuracy when more modes are included, so we can actually distinguish them if they are present, of course. And this is just something that I wanted to remark, especially in comparison with ground-based interferometers, is that higher frequency and therefore higher modes become more relevant than in the other detectors. And just to finish, these are not next steps and future considerations. I don't know if I'm running out of time enough, but I'm not going to go.
We have time.
Okay, otherwise I'm not going to go through all of them. Just let you know that this is just the tip of the iceberg, and we know there is still a lot of work to do, like the inclusion of the precision, maybe higher orders. Also, if we want to study only the ring down, then we have a problem of the choice of the truncation time, and then also maybe introduce some deviation. But if we do how to do it in this inspired major ring down waveform, and how it would affect only the ring down or also the inspired merger part, right? And then, well, yeah, also we need to take into account, for example, for the overtones, the mixing of the modes. So yeah, it's a very broad subject, and we are still digging into it. So yeah, that's all for me. So if you have any questions, I'll be happy to answer. Thank you.
Thank you very much. It was a very interesting talk. So we have time for questions. There's one from Jonas. Go ahead.
Yeah. Hey, Chantal, very nice talk. I had a question about the modes. So you were showing us nicely how you can include different modes and how that changes your predictions. I was kind of wondering about the reverse problem, if you like. So do you know for some likely future source, how many modes can we tell apart? What's the prediction there?
No, actually, that's something that we actually also want to do, right? Because for the moment, we only have 6 modes, so we're dealing only with 6 modes. But how many modes do we need to see, or we want to see? That will actually be determined by the SNR, I assume. So for the moment, we don't have higher modes, so there's not much I can tell you about it.
Okay, but so do you have any intuition at all? So 6 modes sounds quite optimistic for a detection in the future, I guess. But my intuition would be maybe 2 or 3 or so as something we can really tell apart from the data. Does that line up with what you think as well?
I actually think that we need even higher modes. Okay. But this is just my my view, let's say, because actually of what I said, that because of Lisa transfer function, you expect that higher modes to be more relevant. So actually, if you compare with other signals, with other detectors, sorry, these 2 modes that are the 3.3 and the 4.4, they are less relevant. So maybe you don't have to see them. But in Lisa, the 5th mode, let's say, will be here. So you should be able to detect it too. At least when you have the L equal M, well, sorry, the M equal L, right? For the 5.5 or 6.6, let's say.
Right, understood. Great, thanks a lot.
Yeah, thank you, of course.
Thanks. I'm looking at other questions. Yeah, if I can just add a comment on what was just said, I concur. I think well, it depends which kind of source you look at, but supermassive black hole signals can be, if they're nearby, extremely loud, as now 1-2000, And I think the limit in what Chantal has shown here is just what was available in the waveform models that we had to work with. All right, if there are no other questions, I might have one myself. So just to understand, because you should actually, in the first example with your noise, you showed that if you try to analyze the signal without including all the harmonics that you have injected, you actually recover parameter biases, right?
Yes.
And this is interesting in its own regard because it's often considered that these different harmonics, especially if they differ in the value of m, the azimuthal angle, are orthogonal in the sense that they have a dependency as e to the I m times the orbital phase. And as far as the inspire is concerned, say the 2 mode and the 3 mode when you do the inner product between them should be relatively small. They should be relatively orthogonal because they should have very different phasing. But this is interesting because it shows that I think it points towards the fact that the merger and the ring down is so important that the conventional knowledge that you would have from Inspiral does not really apply, and you can actually have cross terms between these harmonics that are not zero. And if you ignore the harmonics, it's not simply that you lose some SNR, is that you can actually have biases. So it's very important.
Yeah, I think that too. And I think that especially here it's important when you add the model of 4 modes. So you actually adding this one here, the 2-1. It gives you also a lower frequency of the inspired power, which I think it's also important for the parameter estimation of the spin, which is you see that, for example, here these modes is not very good, but once you add it, it's a little bit better.
Okay. Thank you. So if there are no other questions here, Sirius will stop here, and
Okay.
we will reconvene. So thank you again for this talk, Chantal.
Yeah.
So we reconvene at 1/4 on the scheduled time to start with the talks of the second half of the session. So thank you all and see you then.